Hello, everyone. Good morning, good evening, good afternoon. Let's start our fourth lecture in our event. But before, I will show you some announcement from our sponsors.
Good morning, my name is Paolo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept, and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere, and space, as well as the processing, interpretation, and dissemination of this information. So what are the activities of the IEEE Geoscience and Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge Data challenges here, which is organized by SpaceNet. We support also community developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the TIE forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and data set. We can meet with other communities and gain from their perspective, and we can build different collaboration, to learn more from each others, and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Thank you, Paolo.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Thank you, Cheryl. So I would like to invite Professor João Paulo Papa from São Paulo State University. Thank you, João, for accepting this invitation.
So thank you, Jefferson. It's my pleasure to be here. And also, I'm glad to be the chair here and to introduce you our speaker for today, and also like to wish you good morning, good evening, good afternoon, depending on the place you are in the globe, right? I think this kind of initiative is very important for everyone and mainly for the young professionals. So I'm glad to present our speaker for today, Professor Jan Wegner. He got his PhD at Leibniz University at Hanover in 2011, and he joined ETH Zurich in 2012. And he also currently he's the head of the Ecovision Lab, and he does research on machine learning and remote sensing, and mainly to solve ecological questions. And also, Professor Jan is the founder and chair of the ISPRS group on large-scale machine learning for geospatial data analysis. And also, he's the organizer and the chair of the CVPR Earth Vision workshops. So I'd like to go forward with the presentation, and yeah, it's your time now. Thank you so much for being here and accepted the invitation.
Yes, so thank you so much, Joao, and also thanks a lot to Jefferson for inviting me and having me in this virtual summer school, which is a fantastic idea, I think, because it allows a lot of colleagues and young enthusiastic scientists and professionals to learn about new trends. And I choose the topic of my talk to be in machine learning for geospatial data, so rather broad, which is an umbrella term for just presenting in the next, let's say, 50 minutes or so, a bunch of projects that we are currently working on and that I think are worth sharing with you. All right, so I divided my talk into 3 parts according to the input data we use. So the first part will be about processing of ground and interpretation of ground level images. And the second part will be on 3D point clouds and depth images. And then last but not least, I will present our ongoing initiatives in research and remote sensing. So let's start with the very first project. And always on the slides, when I start to talk about one of the projects, I put the publication. So if you want to read more details about the projects, just look at those publications. Later on, there's also some unpublished materials, so to just give you a sneak peek into what will be published some month into the future. So our first project that has been ongoing for quite a while with colleagues from UBS 1 in France and Caltech colleagues in Pasadena is this urban object mapping project, where our primary goal was and is today to investigate the impact of climate change and human activities on the trees in cities. And when I started this project, we asked, okay, how are people doing this today? And it turned out that mostly there's arborists, so experts in trees, going out into the streets, basically measuring the GPS position of each tree and then assessing more properties like the stress level of the tree, defoliation, the tree species, and so on. And it becomes obvious very quickly that this strategy does not scale well, which in turn leads to a situation that, for example, in California, the street tree inventories are more than 30 years old and completely outdated. So we were looking for a nice and automated and cheap way to come up with new tree inventories and to track them over time. And what our idea was is basically using Google Street View panorama images. And we are using these Google panoramas here for our project, but basically it would work with any kind of mobile mapping system data. It just needs to be captured from the street level. And moreover, because we in my team here, we do very technical research, we thought it would be very interesting to process multiple views onto the same object at the same time. So, and this is what is shown on this image here. So what we usually have in this mobile mapping system, same in Google Street View, is that we see the same tree, in this case, from multiple different viewpoints. It's visible in multiple different images. And we wanted to use this knowledge not only to detect the tree better, but also to use the geometry that comes with the images when you download them, so a rough GPS position and a rough heading, to constrain the position of the tree better. So the goal is really detect the tree and assign a geographic position to the tree such that you can come up with a map. And our idea here was then that we try to jointly learn the multi-view geometry. So here the two views, but we have up to 4 or 5 views in our approach. This multi-view geometry, together with the warping between views of the same object, instances for robust cross-view object detection. So the idea really is, if we see the same tree from a different perspective, this also can be learned together with the geometry, because the change of perspective on the object depends on the change of the geometry, right? Of the change of the relative pose of the camera. So learning this as a joint distribution, the pose, the relative pose, together with the warping of the object, seemed a good idea to us. And an overall idea was, when you look at this, so this is a visualization in Google, from Google Maps with a 3D view, and you put in the tree T here, another tree T, and then many, many more, and those are the cameras here, C1 and C2, and you have a certain distance between them that you can roughly compute given the GPS data that comes with panoramas, and you have a heading and so on. Then and you look at this figure, you quickly see this can be turned and viewed as a graph. And if you add then more trees and more cameras, it becomes even more obvious that we are dealing with a graph problem here. And since we are in the era of deep nets, we thought it would be great to try something out with graph neural networks. And I will now quickly talk you through this pipeline that we came up with in 3 different steps. This is the overview, and as I said, the full algorithm is then provided in this paper, in the ECCV to 2020 paper. So the first is that we have this input images, so 4 panoramas here, for example. Then we compute the basic CNN features with the backbone, the feature proposal network layer, and then we fuse those features. So this is all part of this object detector step, where we have to detect all trees in all images. And now next comes the part where we have to basically find the correspondences between detections of the same tree across different views on the same tree. And it looks a bit like this. So what we do is that we have a bounding box prediction then, and we classify the bounding boxes, and we set up this graph. And this is a graph example how it could look like. So it's a fully connected graph between the cameras and the trees, and among the cameras, and camera to tree, and tree to all the cameras. And what we then basically do is we do graph convolutions, and at the end we have an edge pooling. So what we do is we basically have a fully connected graph, and then we try to get rid of those edges that are not true. So basically an edge between a camera and a tree, although that particular tree cannot be seen by that camera. And then we get quite many loss functions that all make up the final loss. So we have the classification loss to detect the tree. We have the bounding box regression, which fits the bounding box size to the tree. We have the graph loss here to basically get rid of those edges here also that are meaningless connections. And we have a geolocalization loss, which basically then fine-tunes the position of the tree in geographic coordinates given all the different views on the same tree. Yes, and if we do this joint approach where we learn the relative pose together with the detection of the trees, we can do a lot of cool stuff. So this is an example in Pasadena where we see exactly the same tree, but from with a 90-degree difference in angle. So the street view car basically drove around the corner here and now sees the tree from a completely different side. So if you would want to match those two images of the same tree based only on visual appearance, it's basically impossible. But if we have the rough relative pose that we have jointly learned together with this warping, so with a perspective change, you can detect that this is exactly the same tree. Same thing also if you have very similarly looking trees, like here, the appearance is very similar, so this would lead to a lot of confusion if you would only match based on image appearance. But if you now have the relative pose that comes with it, you see that those trees are not positioned at the same street. Yes, and then of course we do this for thousands of trees, and we also did this for a second data set for traffic signs in mapillary dashcam data sets. And we come up with a detection mean average precision for the trees of 0.74 and a bit better for the mapillary traffic signs. And I have to say that those trees that we miss, they are usually occluded in the images, so by trucks and so on. So you can not really see them, even though you have multiple views of them. And of course, we also have false positives, and false positives are usually objects that look like trees, like power poles, for example, with wooden trunks. And we have a geo positioning error here of the trees of a bit less than 3 meters in Pasadena, and mapillary traffic signs is a bit worse. And this is to a large part due to the poor GPS position that comes with the original panorama images. So if you get something better, you can also improve it. All right. Then we just, for trying for the fun of it, we also wanted to know, well, if we just have those, now the detections of the trees, can we also classify the tree species? And we did a very simple approach, standard. This was in 2000. We did this originally in 2016, so 4 years ago already. VGG16 was the best network at the time. ResNet got much popularity soon afterwards. And we just took a standard image classification approach with the VGG16 network, and we processed up to 70 different species in Pasadena with images then like this, that from the trees that were detected. And we got an average precision of 80% for the 40 most dominant species. And this is what you can see here. So this is a log scaling here. So this is the classes up to class 40. And you see that at the 40th most dominant class, we have a bit more than 100 images in the training data set. Yeah. And this is where you can still see that the average class precision, of course, goes rapidly down. And here until 40, you end up at 80. But if you go then further down, you have less images than 100. It's basically impossible to train a reasonable deep neural net. Even 100 images is basically not sufficient. But still, the cool thing is this is only based on RGB images. So there's no near-infrared, nothing. It's just standard Google Street View images and crops of those, and still you get a very decent accuracy. All right, so next topic is on social media image analysis. And the idea here was that if a flooding event occurs somewhere on Earth, then usually people start tweeting about it, or they put it on Instagram or whatever on Facebook. And the idea was that we just download all of those images of that area, and based on the images alone, we give a rough estimate about the water depth. And you can imagine for this particular case, if you use a learning-based strategy, you don't have any real ground truth. I mean, it's impossible to be in all of those different places at the same time and also consequently. So what we did is basically we looked up what is the average size of the global human, the global adult. It turns out that's 1.70 meters. And then we looked at images with humans, and we always look, okay, what's the water level according to the human standing in the water? So is it up to the ankles? Is it up to the knees, up to the hips, and so on, right? And based on this level definition, we then also translate that scale to other objects, so children, cars, buses, trucks, bicycles, buildings, and so on, and that we have as objects, and we quantify the water level. And then we basically come up with an approach that is based on the well-known mask RCNN approach, which is an instance segmentation approach, but we have several different refinements that we add to it. So this is an object detection loss that is part of the original loss, and it's instance segmentation. So we distinguishes different instances of the same object class, like different humans in the same image. And then we have this object class specific water level loss, which basically looks at how much of a particular object is occluded. And then we minimize the combined loss, which basically tells us, okay, a water depth per object instance. And then we have a post-processing step where we have all the different water levels per object instance. So this is shown here. So for example, this human here sitting on the front of the car, and is correctly assigned water level 0 because this human is not touching the water. There's nothing of the human in the water, so there's no evidence about the water level here. And those are all predictions already on the test set using this deep net approach. And this is what water level 2 for the car. And then there's again, this is water level 5 for this adult who's pulling his family in the boat. And those people in the boat, the child and this older, or this woman, they are correctly assigned water level 0 because again, they are not touching the water, and as such, they don't have direct evidence about the water level. Yes, and if we do this, and we then have basically we compute the trimmed mean across all of this water levels, and we do this for 1,200 images, and after cross-validation, we get the mean absolute error of around 8 centimeters, which is rather good. So if you want to first estimate, and you only of a certain water depth in a region, so just, let's say, can the Red Cross drive your trucks and so on, this is pretty good. All right, so next slide is then on 3D and depth. So this is a point cloud. So we look at point cloud matching and 3D key point descriptors. And what we want to do is that we want to register two different point clouds that overlap with 30% or more automatically. And the idea here is that we use a so-called smooth density representation to learn descriptive key points in the point clouds that generalize across different scene layouts and sensor modalities. So you can basically train on a LiDAR point cloud, but still use the model to match RGBD depth images and so, for example. And we call this 3D SmoothNet. And the cool thing about it is that it has very low dimensional, highly descriptive feature vectors compared to most state-of-the-art. And they're rotation invariant, and they are what I just mentioned already. They generalize across different scenes and sensors, which is also fantastic. And I will just quickly talk you through how this actually works. So what we do is first, when the raw point cloud comes in, we extract a spherical neighborhood around each interest point. Then we estimate a unique local reference frame based on a singular value decomposition of the covariance matrix, which is pretty standard Then we transform it to its canonical representation. And then we voxelize it into smooth density representations with the 3D Gaussian smoothing curve. And then we basically normalize the smooth densities. And then another trick on probably good engineering is that we use a so-called soft margin batch hard loss. So just to explain this, so the input are 2 point clouds. So those are the 2 point clouds here on the right side with an overlap of at least 30% as smooth densities. And the output then, after all the processing, is a very compact local feature descriptor for those points. So what we do is that we randomly sample 300 anchor points. So those are these round points here of the overlapping part. And the next is that we also do this transformation with the other point cloud. Now this is for the training case. And we sample, positive sample as nearest neighbors in feature space. And if you look at those points, then if you cut out the cube, around those points, this is what it looks like here in the first point cloud. This is in the second point cloud that we are basically transforming to this one. And the interesting part is now this loss function here, which is this soft margin batch hard loss, where we have the anchor points here and here. So this is what we also see here. So the round points are the anchor points. This again here, top right, are the anchor points. And then in this part here, we have the positive samples, and we try to minimize the error in feature space between the anchor points, so these ones, and the positive samples, so these ones here. So we minimize the error between this part of the point cloud and the same place seen at this location and this one. And then we also, and this is this batch hard the part, then we also try to push away the negative samples as much as we can. So we take the negative samples that are the hardest non-corresponding samples, which means that we basically want those points of the second point cloud that look the most similar to those ones here in the first one, and we want to push them as far away as we can in feature space, and then decide them. And this is what is then shown here. So those are the negative ones, those are the positive ones, and those are the anchor points. And if you do this, this is a rather powerful strategy. And we did this for several data sets. And this is the well-known 3D match indoor RGB depth data set from Princeton colleagues. And if we do this and compare the performance to the state of the art in 2019, I must say, so last year, is that ours outperformed state of the art by more than 20 percentage points. So which is great. And then even if we train on 3D match, so this RGB depth indoor data, and now we test on a data set that is captured with a terrestrial LiDAR sensor and outdoors and in the forest, so in vegetation, so there's no retraining here, then we are still very good. And this is cool because it shows that the model generalizes very well, which is due mainly to the smooth density, because the main trick here is of the smooth density representation of the point clouds is that before we give the point cloud to the learning engine, to the learner, we basically do a lot of smoothing on the point cloud and get rid of a lot of outliers and so on in points, such that the network itself does not have to learn it. Because this is what we found usually the first thing that the deep nets for point clouds do, that they learn a smoothing in the earliest layers. And now this is done prior to processing. And then all the training data that we have can be used for the deep net to learn strong descriptors. And this is, from my point of view, the major reason why our approach outperforms all others by almost by more than 20 percentage points, and also why it generalizes. Yeah? Because if you smooth the LiDAR point cloud and use it for training, or you smooth an RGBD point cloud or depth image, that doesn't matter so much. Both of them, if they are captured of the same scene, will look rather similar. All right, so second topic on depth data. This is work on guided super resolution, and the idea is that we want to increase the resolution of a depth image, so such low resolution source image that is, for example, captured with a depth sensor and then a smartphone or a Kinect sensor, using the high resolution data captured with an RGB camera that is on the same sensor. So we want to get a much more high resolution depth image. So this one, so this is what we want to get. This is our target, given a very low resolution source of the depth plus a high resolution RGB image. And this is an extremely ill-posed problem. And our idea is different from what is out there at the moment. And the idea is basically that we translate the guide image, so this one, to the target domain directly. So we directly learn what RGB value relates to what depth value. And then we constrain the result by matching it back to the source image, to this downsampled image. And this is, again, so how it looks like. So we start basically from the RGB image, and we train a direct mapping with a deep net of each value here in the pixel to the depth value, to the target space. And of course, this wouldn't work very well. We would get a lot of noise and so on, because color alone and even a bit of context does not tell you enough about the depth. So we need a very good constraint. And the constraint is basically, if we then downsample this image, then the average value inside a particular patch that has the size of the original resolution of the source should match to the depth value here. So that's the constraint. So we downsample then this image and match it to the original source image during training. We downsampled. And the cool thing is that this translation here, it operates per pixel. And also the constraint is per pixel. So we don't have any upscaling. So it does mean we have no blur in the image. We can keep sharp edges, and in contrast to state of the art. So this is then how we implement it. So to get this depth target image, we basically formulate it as a multi-layer perceptron, but we can then turn it, if we introduce convolutions, to a fully convolutional network. So CNN basically, one by one, IC filter kernels, and because we can do this, we can then use PyTorch or TensorFlow, so very efficient parallel deep learning frameworks. And as I said, so once we have this direct mapping from pixel to target, so from the RGB image to the depth image, we still have to constrain it. So this is then put here, and we still have to downsample it and make sure that the average across a certain patch size matches the original depth image at lower resolution. So if we do this, so here's again the input, very low resolution image, and this is the guide. So that's the depth input image. This is the guide RGB image. And this is the target. So this is what we want to achieve. So that's ground truth here. And if we look at ours, so this is a result that we get. And the performance is measured in terms of mean squared errors. So we have this one, and then we compare to several state-of-the-art and baseline methods. So the simplest way to upscale get improved resolution of such cost is, of course, like a bicubic interpolation, just without any RGB image. So this doesn't work very well. Then there are several other baselines, but in terms of numbers, they are much worse. And you can see that they get very blurry. So our trick of mapping directly RGB values to the depth values, and then only afterwards constraining it to the lower resolution of the depth image, seems to work quite well. But what you also see is that we cannot get rid of a little bit of artifacts that depend on the texture. So still a bit of texture, which doesn't tell here, this doesn't directly correlate with depth, is transmitted to the depth image. So this is, of course, something that you would want to avoid, and it's about future work to decide on how we want to proceed here. Okay, so now moving to the last part of the talk, which is on remote sensing. which also makes up a large part of the research that we are doing. And the first one was that I have basically, since my PhD times, worked on semantic segmentation of aerial images, of synthetic aperture radar images, or optical aerial images, or satellite images, and always with the motivation to basically make maps. And it really struck me, and it bothered me that we only always do semantic segmentation and stop there. And if we want to transform this pixel map into a real map, a vectorized map, so into polygons that we can upload to the web, share via mobile phones, or use in a GIS system, you need a lot of different post-processing steps. So I don't know, some Douglas Polk algorithm to vectorize your raster outputs, and so on and so on. And then this gets, again, a very hierarchical procedure, very interactive with a low degree of automation. And my idea at the time was, why can we not bake everything into the same end-to-end learnable deep net framework? And that's actually then what we did. So the idea is really that given an input aerial image, we directly want to output a vector map, so polygons that you can directly map in use in a GIS system or upload to OpenStreetMap, for example. And we were inspired by Polygon RNN at the time, so the Waterson and Fiddler groups in Toronto. And we're leaning a bit on their ideas how to implement it. So, and this is then how it looks. So basically what we have is that is object detection, so buildings and road in our case. And we have instance segmentation, and then we have vectorization within one unified approach that relies on CNN married with a recurrent neural network with convolutional long short-term memory. So it's basically a convolutional LSTM approach. And the CNN takes as input an image, and in order to transform the image to the polygon representation, what the CNN does, it basically detects the key points. So those are corners of a building and edge evidence of the building footprints in the road networks. And this is how it looks. So you have the standard CNN backbone that computes all these beautiful features. And what you then have for training, so you try to get here the edge features for the boundary mask. So you have try to get the edge evidence here, and you have a vertex mask that comes from OpenStreetMap also, where you try to detect the corner points. And then once you have all the corner points, and we do the same for the road, so we extract the center axis of the road, and we get also all the vertices of the road, so where junctions are or where a road is leaving the image. And then one by one, we pass each vertex to the RNN, which then tries to connect all these different vertices into a unified polygon. And this is what it then looks like. So you have the image features of the CNN, and they are fed sequentially to this convolutional LSTM. So you as at road, for example, you go through all the different vertices, which is shown here. So here's one, here one, here one, here one, here one. And you try to connect them with the RNN into a polygon representation, a graph in the end, a vector representation. We do the same for the buildings. And we start at multiple key points. And because then the question is, okay, at the building here, where to start? And then sometimes it might happen that the wrongly nodes are connected that go through the building and so on. So our basically engineering hack to deal with wrong connections was that we start at multiple different key points at the same object. So this one, this one, this one, and so on. The same for roads. And we generate an over-complete set of building object hypotheses, the same for roads. So we basically have multiple different shapes, multiple different versions of the same building. And we then condense all these multiple different polygons into one final representation using beam search. And beam search is a well-established heuristic method in the machine learning community. Yes, and if all of this works nice, then those are the outputs. So we have this vector representation polygon of the building and the polygon of the road. And here are some results. And we did this for a very large data set that we came up. So for buildings, we have we computed this for 3 million buildings and for almost 9,000 kilometers of roads. And this is a typical output that you see. So we compare it to baseline and state of the art. So if you use mask RCNN, so a very good method for instance segmentation to PANET, you see this is the pixel-wise presentation. So each pixel is annotated. And here we only have the vertices and the polygon. And since we know what kind of vertices they belong to a building, we can just fill it. And this is then the only representation is directly polygon. The cool thing about the RNN is that we implicitly learn priors on the angles here, so that 90-degree angles are preferred. In contrast to standard semantic segmentation, DeepNet, or also mask RCNN, where you only have very local connections despite the large receptive field of the CNN. And there you don't have this general prior on the sharp edges. But in the polygon representation, we have this abstract prior that we learn implicitly. Yes, and we do the same thing for road and compare it with others. So road tracer at the time, for example. So this is the ground truth graph. The blue vertices are connected with with these orange edges. And road tracer, you see, has a lot of different vertices because it's an incremental sequential approach, while ours has a very lean representation. So road tracer result here is almost, if you want to use it directly in the GIS system, it's basically impossible. And this is our representation. So of course we do miss some edges here, but in general it's quite okay. And then if you evaluate it, it also performs quite well. All right, so moving on to now topics where there's a strong focus in my group now is on environmental problems. So the idea is to really investigate, do top computer vision research and machine learning research on a very technical level to solve environmental problems. And what we have here is that we basically want to map oil palm plantations. So you probably know that oil palms are very controversial. On the one hand, of course, they produce a lot of fat that is desperately needed for any kind of production, chocolate, for example. And they use relatively little space to do so. On the other, and they also are a very valuable cash crop, so to speak, and provide a great economical opportunity for people, like, for example, in Malaysia and Indonesia. On the other hand, it's well known that this monocultures and plantations destroy a lot of rainforest and biodiversity, and there's a lot of illegal deforestation that is happening. So they destroy a lot of precious nature too. And to just such that we know and understand what's going on, to map all these oil palm plantations, we have to know where they are, how dense these oil palms are planted. And our idea is now that we want to count all oil palm trees globally based on Sentinel-2 images. Because Sentinel-2 images come for free, they come every 5 days, which is great in the tropics. Because even if you have clouds, then at least once a month, every 2 months, you get an image where you can actually see something. The difficulty here is that, of course, one tree, so one oil palm here in the image, is much smaller than the pixel on the ground of a Sentinel-2 image, so which is a 10 by 10 meter pixel, and an oil palm is approximately 1/3 of that. So the idea is then we cannot use object detectors directly. It's totally impossible. So what we do is we turn tree mapping into a density estimation task. And this is what we then do. So we basically combine this identification of the tree species, so detecting or semantic segmentation of palm oil trees, and we also do it for coconut, and counting them, so really understanding how many oil palms or coconut trees are below one single Sentinel-2 pixel. We do this, we formulate this as a simultaneous task. So because this evidence from the semantic segmentation and the counting task are mutually reinforcing. So we have the semantic segmentation with a specific loss function, and together with the density estimation task, which is a regression loss function. And we combine both to have both. So we have, in the end, we know where palm oil or coconut is growing, and we know how many trees are under each pixel. And this is just then a result, for example. So this is a ground truth. We came up with ground truth based on Google Maps aerial images, where we really manually were sitting down, labeling a few images, and then we were training an object detector on those high-resolution images to get more and more ground truth. And then this is a prediction once we train our model for density estimation. You can see that, of course, it looks a lot smoother because the resolution is just much worse in the Sentinel-2 image. But still, it gets the areas quite well, and we will also see that it counts very well. So we did this for coconut and palm, so oil palm and olive trees in Spain, and coconut and palm in Indonesia, Malaysia, and the Philippines. And our data set is we had almost 90,000 coconut trees and more than 140,000 oil palm trees, and we could count those trees with a difference of 4%. So we got very close. And we did this for a test region bigger than 200 square kilometers. And at the moment, we are scaling this up, and this is a first sneak peek to some new results that will come out and will be submitted for review soon, is that we want to do this palm oil density maps now for whole Southeast Asia, and then also compare and track over time how did this change over the years. Okay, so now I'm slowly coming to my last part of the presentation, which is a bigger project where we want to estimate canopy height and biomass at global scale. So at the moment, if we want to estimate canopy height, what is done usually is that we have very expensive airborne campaigns, or we have spaceborne campaigns like ISAT and ISAT-2, but very often for biomass, what we have is in situ surveys. So our colleagues from the environmental sciences, biologists, go out into the forests and estimate the biomass. And this doesn't scale. If you want to estimate a biomass map or canopy height map at global scale, which are very important for climate modeling and the modeling of climate change, and also estimating biodiversity at global scale, these are super important input variables, then you cannot do this based on in situ data alone. And our idea is now here to basically do this based on optical satellite data. So we want to develop an accurate, scalable approach using Sentinel-2 satellite images to estimate canopy height. And the basic component here is that we basically separate the spectral information about the canopy height from the spatial context, so textually the images. And we use this Cholet at CVPR 217 approach, where we have separable convolutions. Another thing is, since we are moving away from computer vision images and terrestrial images and have rather low resolution images, one thing is that a lot of the standard computer vision architectures cannot directly be applied to our sort of medium or high resolution imagery. So we have to get rid of all the down on up sampling. We no longer have this bottleneck architectures like UNet, like architectures where you first down sample and so on. And we also have no max pooling, because then we lose too much detailed information. And on the other hand, we don't need it usually, because we don't have to account for this this big scale difference in objects like we have to do when we see a car in a computer vision image. That can be small when it's far away, can be very big when it's close to the camera, but we don't have to do this here because the satellite always flies at the same altitude. So we basically, again, designed this architecture, CNN, and input is a Sentinel-2 image, and output then is the estimated canopy height. So we directly regress the height using a very rather simple Euclidean loss function for regressing continuous height values. And we have an L2 penalty term here on the model parameters, which is as a regularizer, which is called in deep net terms is called weight decay. And you have the number of pixels here is n, you have the vegetation height predictions here, and you have the ground truth here. And then you have the model parameters here, and the number here. And we do experiments where we have reference data. And at the time when we published this work, we didn't have so much. So we had the reference data for whole Switzerland. So we have 2 regions of interest in Switzerland. And we got 5 different reference data areas from full waveform airborne LiDAR data from our NASA colleagues in Gabon, which is a country in West Africa, which has a lot of very dense native rainforest with very high trees, so up to 65 meters. And when we apply our model, we plot the ground truth versus the prediction, and if everything is perfect, everything should be on the diagonal. And of course, it's not completely perfect, but we see that the results are rather nice. We get the mean absolute error for Gabon of 4.3 meters. And in Switzerland for below 2 meters, but also, of course, the trees in Switzerland are smaller, so up to 35 meters, where in Gabon they are much larger, up to 1665 meters. And if we plot the error here, so the Gabon is in green and Switzerland is in blue. So in Switzerland only goes up to this interval. We plot this error per interval. We see that the error for Switzerland is increasing with canopy height. And usually this is also the case, especially for the very late, very high trees. We see that after 40, 50 meters, our method saturates. So if we look at trees above 60 meters, and there also we have almost no training data because they are very rare, we get very high errors. And we also found then, by the way, that we had gross errors in the Swiss ground truth. So the Swiss ground truth is based, for vegetation height, is based on subtracting a digital elevation model from a digital surface model, which are both, the digital surface model is acquired through a multi-view stereo matching from airborne imaging campaigns. And what we found is that there are very big errors, especially at steep slopes, which is due to a mismatch of the DEM and the DSM. So actually our method is a bit better than what is shown here. So some results visualized. So this is a NASA map of Gabon from the paper last in 2011, and color encodes vegetation height. And this is our map. So NASA has a spatial resolution of 1 kilometer. We have a spatial resolution of 10 meters, so much, much better. And then in this white box, this is a high resolution visualization now. And we can see that in our method here, especially in this delta where we have a lot of mangroves, very high mangroves, up to 60 meters, we get all the fine-grained details very well, while this NASA model basically misses all of that. And in Switzerland, again, the existing NASA model then has a strong bias because it's a very mountainous terrain to overestimating. So here in Engadin, for example, it's basically assigning 40-meter high trees, the NASA model, to in very high alpine regions, which is completely wrong. And then we see our model here at the same place is much more accurate, so it gets most of the vegetation heights really nicely. Yes, and then now we are working on scaling this globally, because you can imagine for deep nets, you always need the ground truth and reference data to train your models. And that was a big issue. And we thought, okay, how can we get around this thing? And then we got to know this NASA GEDI campaign, which is a campaign of NASA, where they put a full waveform laser scanner on the International Space Station. And it's a full waveform thing and meant for vegetation height, so canopy height mapping and biomass estimation. And this is just a video from NASA GEDI of the mission. So this is the ISS that you can see. And the instrument is here. So this is the module to have payload on the ISS. And this is the payload. Here is the laser. It has those laser beams that shoot all the way down here. And 8 different laser beams with a certain distance. And there's a gap in between. And it scans then along these tracks. And each pulse is like it's sent out here. since it's a full waveform, gets usually more than 1,000 returns. And so this is the ground here, and this is the canopy height, and this is the height plotted here on the y-axis, and on the right axis, on the x-axis, it's plotted the intensity with what the reflections come back. And you see that there's a lot of energy coming back, of course, from the top canopy. So this is the first peak, and then it's getting less and less, but you can still see it follows the vegetation structure down to the bottom, and then there's quite a peak at the ground again. And what we now want to measure with our model is basically the difference between this peak and this peak to get the vegetation height. Okay, so, and it turns out that, of course, if we want to, so first thing what we wanted to do, we just wanted to take the product that the NASA GEDI team is producing, so they have a product on vegetation height directly. But we compared it to our reference data in Switzerland and Gabon, turned out that it was just very inaccurate. So what we then is that we reached out to our NASA colleagues, Ralph Dubaya and John Armstrong, and we said, look, what if we try to recalibrate your GEDI data and with a machine learning approach, which is what they didn't do. So they don't use machine learning. They have a mechanistic approach to model this, which is then different for different places on Earth. And we wanted one single deep net approach for the entire globe, for the entire Earth, for all the data, no matter if it's in Africa, North America, Europe, Australia, South America. And at the same time, it's very important, especially in the environmental sciences, but for many other fields also outside computer vision, to assign probability or an uncertainty to the output values. And if you are a bit familiar with CNNs or deep learning in general, you know that deep learning per se is not a probabilistic approach as opposed to maximum likelihood or random forests and so on. So what we do is so-called Bayesian deep learning, which is a new and exciting field that we should look much further into. Which combines the power of the prediction accuracy of deep learning with the interpretability and the uncertainty estimation of calibrated uncertainties of probabilistic approaches. So what you then basically do is you get this raw waveform as input, and we train an ensemble of CNNs. So we have 10 different CNNs. All are trained separately on the same data, but with random initializations. And we have 2 outputs per model to approximate the conditional probability, so the mean value and the variance. And then we minimize the Gaussian negative log likelihood, and we optimize over the CNN parameters with the stochastic gradient. So this is a loss function per CNN. And then if you do this, you can combine the outputs of all this. So this is the output per model. So, and you can, for canopy height, then you get all the different outputs per model. So this blue, for example, from here, this one from here, this one from here. And you basically try to approximate the Gaussian through these different outputs. And this is what is shown here. And it's what you then do this comes from Alex Kendall's paper from 2017, his Oxford group, is this, that you model 2 different parts of the uncertainty. So one is called the epistemic uncertainty, which is the model uncertainty, and the other one is the aleatory data uncertainty. And you come up basically with one final output, a prediction, and an uncertainty estimation. So if you do this, and now this is very new, this is all new, it's unpublished material. So this is then, if you do this, train the model on the reference site that our NASA colleagues gave us, and you validate it, and then you apply it to the whole Earth, and this is what you get. So this is the canopy height of the whole globe. So let's say, except in northern Canada and a bit of northern Europe and Russia, northern Mongolia, and so on, because the ISS only flies up to here. So if you then plot the canopy height at 0.5 degree resolution, this is what you get. You see a lot of very high trees here in Brazil and the Amazon area, here in the tropical regions of Africa and Gabon. Gabon is here, and in Congo here, and also in Indonesia, Malaysia, and so on. And also very north here, there's all those redwood trees around in the state of Washington, around Seattle. And another interesting thing is we can then also for each prediction assign the predictive standard deviation. And when we plot this, we can see the standard deviation is between 0 and 6 meters. Everything above 6 meters is also clipped here. Then you get this map, and you see that the standard deviation basically increases with the height of the tree. So in the very high tree areas, you get also higher standard deviations. In other areas, it's much lower. All right, so this is the end of my presentation. I hope I could show you quite some interesting projects. And I want also to say that, of course, most of the work is not done by myself. So this is my team. In the meantime, it's bigger even, but it's all thanks to them that this cool stuff can be researched and worked on. For example, Nico here, he's working on that vegetation height mapping project that I just showed, while Andres is working on the oil palm density and so on. So this is a fantastic team, and thanks go to them. Some exciting or two exciting future directions that we're currently working with, that we try to combine deep learning with physics-based modeling to get rid of a lot of training data and make our models more interpretable, and graph CNNs, more research on that. So geometric deep learning, also use it for remote sensing on more environmental sciences approaches. All right, so thanks a lot for listening, and I'm looking forward to your questions.
So thank you, Jan, for the nice presentation and exciting results, actually. Before going to the questions, I'd like just to give some comments here. Actually, in I don't know the past month, I guess, I was wondering. I have seen some works. They apply it. They're concerned about shallow networks and mainly on low resolution images. And I think that the number of works are like they're increasing because most of the time we don't have a lot of data. We don't have computational resources. Like sometimes the winner is just the guy that has data, right?
Yes.
Or more computational resources. And you know that companies like Facebook and Google, they have that kind of thing, right? For you, I mean, and also it seems that that kind of companies, they are more concerned about problems related to biometrics, face recognition, and computer vision stuff, right? Do you think that we have many industries working on remote sensing thing? I mean, and also the other question is, should we consider to work on like shallow network, thinking about neural architectures that can be embedded on board systems and this kind of thing? What do you think about it?
Yes, so I absolutely agree with you. So the first point is that a lot of the, let's say, top CVPR papers or ICLR and so on, and NURBS papers, they need a lot of computational power that in academia we don't have it, or then we really need to bet on this one single project to get all the numbers right. I must say that we, of course, at ETH, we are lucky we have a supercomputing cluster and so on, so we can still do it. But as a personal point of view, I must say, as soon as it's only about squeezing the last, I don't know, 0.2 percentage point out of a method, and you use, I don't know how many GPU hours and years for that, as an academic, I'm no longer interested. I think this is incremental. It's not interesting. It's not a new invention. It's not the method by itself. I can happily leave it to Google and Facebook. Yeah. So it's even not that I don't want to compete. I think it's incremental research. Yeah, we are scientists in academia, and I can understand the companies. I mean, they need to make a product work. They need to squeeze the last bits of accuracy out of it. But we in academia, I mean, we are there to do moonshots, right? So we have to come up with new and bright ideas. I don't want to, we don't need to or should waste our creativity, time, and energy on tuning those numbers, increasing that. So I think it's better to look into really new directions, new algorithms, like, I don't know, marrying physics with deep nets or graph geometric deep learning and so on. And yes, so that's my view on that. Then the second point is remote sensing. I see now more and more that there are very capable remote sensing people with a strong machine learning background that really do cool research in machine learning with using remote sensing data as a data set. And I think it's a bit a natural development that first breakthroughs were on computer vision images because they are just much more available. They're also easier to annotate. Yeah. If you have something like Amazon Mechanical Turk, you download, I don't know, tens of thousands of vision images from the web. That's very quick. And you give it to Mechanical Turkers to annotate. That's also very quick. Then it's a much quicker process. In remote sensing, for a long time, we didn't have the situation. I mean, we didn't have this data for free. Now it's coming more and more. And we also didn't have this massive amount of sensors up in space, which is also changing now, right? And then also, for a long time, only few people from our community had access to a lot of data because it was very expensive to acquire. But this is rapidly changing now. And I see that this is moving more and more into a direction where also we, as people with a remote sensing background, or the other way around, people with a computer science background, get interested and can marry this to communities. I mean, I've been organizing this Earth Vision workshop now for the last years, and from the first edition on, together with Davis Tuya and other friends and colleagues. And I see that this has more and more impact. And also because I see that a lot of people from the vision community are tired on working only vision images, because a lot of the big companies are taking all the let's say prizes and awards. For them, it also gets interesting to look more into remote sensing data, because it's something that is a bit less explored. There's still a lot more challenges. I mean, for example, data annotation, how to label things. If you move away from the standard objects that are in OpenStreetMap, it gets very hard. For example, in my case, biomass. You cannot annotate biomass based on an image. So you need to be there. You need to do something about it. And exactly that, so collecting reference data becomes more and more of an issue there. So, and this now comes to your third point, is I agree, like looking into new ways, more shallow networks, cool physics constraints, looking also into, I don't know, physics simulations like DART or something for ray tracers for this kind of stuff, and marrying forward simulation of remote sensing images with deep nets and so on. I think that's cool stuff. And I think there's a lot of things that we can do from our remote sensing perspective, where I would hope that we are also, at least now, still a bit ahead of the whole machine learning and vision crowd. So yes, so I hope I answered most of your thoughts.
Yeah, no, just like to start this kind of conversation and then, you know, like shed light these to our young students, and, you know, just to enlighten them with these kind of questions. And, you know, that most of, you know, have a lot of works, they are data set oriented, and we must give our attention to the research as well, not get only focus on accuracy, you know, this kind of thing. Just like this kind of provocation. But yes, and then so let's get started with the questions, and also like to introduce you, Professor José Quintanilha. He's our invited researcher from the University of São Paulo, and also Matheus Barros. He's also our invited student from the University of Minas Gerais, right? So I'd like to welcome you all to the session as well. So I think we have a couple of questions here, right? Yeah, João, you wanna Giuseppe?
Thank you for the invitation. I enjoy very much the presentation, a very didactic presentation, clear. I enjoy very much. And I would like to grateful to the Jefferson and the coordinators of the event for this opportunity. In fact, after see your presentation, many questions could be formulated, but I will focus in a special case. Today, we call small objects, mainly in urban features, like a landscape, objects on top of the roof, urban flooding, traffic sign, etc. How deep learning or machine learning can help the analysts? In this case, I think the probabilistic approach could be better than the deep learning approach.
Yes, I agree that for a lot of real-world applications and a lot of research outside the vision community, probabilities or uncertainty estimation that that comes with the predictions that we make is absolutely essential. Yeah, I would never go to the Red Cross and say, look, this is my water depth estimation or my map of the water flooding from a deep net. But I cannot tell you how much can you trust it, right? So frankly speaking, I think then it's useless for them because it's putting lives in dangers, and also they need to be very sure about everything that we give them. And I agree that if you have not much training or something, just starting with established methods, probabilistic method like random forest, for example, that's an absolute good, perfect approach. Right. But I wanted to make the point here also in the last part, and we are going more and more to this direction, that there are new ways of marrying or integrating both worlds. So you can, in the case now we did this for the GEDI sensor, have a deep learning engine and still have very well calibrated uncertainties. Because although it's not a probabilistic method per se, it's about calibrating the output scores of a CNN. So, and they are usually the output scores of the deep nets or CNNs, they are either overconfident or underconfident. Something in between is not happening. And one way is the way that there are multiple different ways, but this ensemble approach with this particular loss where we estimate the mean and the variance, and then you combine it using aleatoric and epistemic uncertainties. And those uncertainty estimates are very well calibrated. And there are several methods to test and to verify it, because we don't have ground truth for probability values for obvious reasons and for remote sensing. But there are several ways where you can actually verify that they are very close to the true uncertainty estimates. And we also saw this in our GEDI predictions now, because in our training data, for example, we have only trees up to 70 meters height. But in the real world, we have much higher trees, above 100 meters. And our model can predict those trees, so it sort of has to extrapolate, right? Although those trees has never seen such high trees in the training data. And we see, for example, that that the uncertainty is very high for those high estimates. Although we see when we look them up that it's rather accurate. But there's a lot of, so we can see that this combination of deep learning and uncertainty estimation is very promising, and I think is an exciting field to explore. On the downside at the moment is what we do is, I mean, we have to train 10 different CNNs, yeah? So it's computationally super expensive, and this is, of course, a bottleneck. So we need to get rid of that. That's a problem. And I think it would be exciting if we as people with a, let's say, not only vision background, but remote sensing, and that we are used to working with uncertainties, we should invest more time and energy into creating novelty there, and to marrying our world of probability theory, uncertainty estimation, and so on with deep nets. I think that's very promising.
Okay, thank you. Thank you. Can I make one more question? Mateus.
Well, I'd like to thank the team first for the invitation and thank Professor Yan for the presentation. It was great. Many interesting topics and applications. I have some questions here, but I see that everyone that is watching us, they also have some questions, so maybe we should give them some attention. Here we have a question from John Davey Perez Arguello. How to face the difficulty of detecting objects with CNN in high resolution images like 2000 per 2000 pixels or more?
Yes, so what we do is, so the first thing is you can basically tile your image and then stitch the tiles back together after you have processed them. So you basically have a certain stride when you move across the image, and you basically you tile the image basically and put those tiles back together. That's sort of, I would say, good engineering that is also built into PyTorch libraries or TensorFlow. So if you look for remote sensing, also other works, we have implemented this here, for example. Of course, if you are looking for something where you have a receptive field, right, of 2000 by 2000 pixels, I mean, you need, so you really want to learn all of that. You need to look for some non-standard CNNs. For example, one thing is use some form of graph CNNs. So you no longer operate on a pixel level, but you look for key points or something like this. And then there are other variants that completely go into novel research. Some ideas from the top of my head now is that you do some sort of multi-scale approach. You go for lower resolution first, and then you have separate streams, like with sort of an octree representation. Look for more high-scale features and mappings when you get more fine-grained evidence. But I think that's if you really want to have a single, let's say, operator, a CNN, that has a receptive field of 2000 by 2000 pixels, at the moment, if you have a dense image, you cannot process it. At least we cannot. So yeah, graph CNNs, some hierarchical approach, I would say.
So that's good. So I have one question here from Luis. So do you think the Connect sensor can be used in the super resolution project for detecting indoors cloud of view instead of LiDAR? Well, and then I got another question, but you can go with this one.
Mm-hmm. So I'm not sure I understand this cloud of view, but so in general, I mean, that's what we did, right? So we used the Kinect sensor indoors, and that's the result I showed, and other data sets and so also do this. So in general, if I understand the question correctly, it's about if we can basically replace LiDAR, very accurate measurements, with a standard Kinect with a lot of noise indoors. And in general, I think yes. So for a lot of applications, if you do not want very accurate measurements, you can just use the Kinect nowadays or newer versions of depth sensors and use the super resolution approach. Absolutely. I mean, also this is some stuff that is built into some smartphones already now, like Huawei or Apple and so on. So you can absolutely do that. Of course, if you want to measure super accurately also distances and so on for some reason, then I would still use a LiDAR sensor. But for standard visualization or interior architecture or whatever, or getting a rough estimate of the layout of the room and stuff, that's completely sufficient with the Kinect and the super resolution approach.
Yeah, right. And actually, I was wondering when you presented your work related to super resolution, right? And then you have that's a cool thing. I mean, from a low resolution image, you have another high resolution image from a different domain, and then you can do the super resolution thing. And then you mentioned something about some artifacts related to the texture of the guide image, right? So have you analyzed the influence of the guide image, or can we? How is the proper way to choose a guide image, or can we use a set of guide images to have some sort of, I don't know, an average image, this kind of thing?
So, I mean, in general, yeah, it's hard to say. I mean, the larger the training data set is that has multiple guide images in them with any kind of texture, the better the model gets and the less texture will get transferred. So then in general, of course, there are a lot of cases where you can just not get rid of it. I think in general, for this approach to get rid of the texture, of course, the best thing is use an image without texture. Yeah, so with just plain surfaces like you see behind me on the wall next to the poster. Yeah? But then, of course, sometimes you would also get in trouble with the depth image for those places, but because then depth images might also not be so good. But yeah, and so yeah, I think it just needs improvements to the method, honestly, because the way we do it now, that we directly predict from one pixel or like a neighborhood, also the depth is just prone to artifacts by texture. So you need to explicitly probably build this in through the loss functions to disregard any RGB texture. You need to learn that and these things. So my first thing would be to put it into the loss function. Then you might also think about some, I don't know, deep supervisions or some intermediate losses that really try to distinguish between the object, surface, and texture already in the RGB image. So you really try to discard in the network at an intermediate stage the texture and try to distinguish from the rest of the evidence. But this is just some ideas. Yeah, we haven't done it, but you can do it.
Yeah, and also maybe we said something, but your guide image was like it's real or synthetic one?
It's real. So the guide, so it's a real data set.
Right.
I have to go back to the paper, but it's like the NYU data set, it's benchmark data sets
Right.
of the computer vision community. But we also, it didn't show it. We have it in this this ICCV paper also. We have a completely a second data set in remote sensing. So there we did basically super resolution for vegetation height mapping based on satellite imaging. So there it also works, but we see the same thing that also some texture, let's say some stuff that is not some roads and then fields next to it, they also transfer a bit to the super resolution depth image then, although they have the same height or depth in real world.
Right. Right. Yes. So let me see here. Jose, you sent us some nice questions by email, right? Do you want to try?
Yes. I would like to make another one. In your editorial from the special issue of the International Journal of Geoinformatics, you mentioned there is a need to share data in source code publicly. How this issue is being addressed by the international community, particularly in the case of the crowdsourced data? There are some guidelines to avoid the legal problems. I don't know.
Yes, I agree. I think we should really push in our community for open sourcing data and source code. And we try to make this possible whenever we can, especially in remote sensing. And for a long time, from my point of view, it was a good tradition that each group had its own collection of satellite images, would not share it, and then publish a lot of papers with that paper. No one could ever check or prove whether the improvement publishing the papers is due to just them having access to the data set or if it's due to the method. So I think it needs a lot of effort in benchmark data sets. And we made some effort also the IEEE GRSS data fusion content. So I think this is on SpaceNet also very valuable benchmarks. Also we had ISPRS benchmark sets, very valuable. But also us, when we publish papers, we should make our data available. Although this is sometimes hard because it's massive amounts of data. So for example, what we do, we cannot put everything on the server, but the source code, when we are allowed to and not bound by any constraint by any partners, then we put the source code online. If we haven't done so for some papers, then we're still cleaning it up. Or if it's not available on the website, everyone out there also listening today, email us and we will share it with you. So this is what we do. I see a point, though, like massive amounts of, let's say, Sentinel-2 images, for example, if we want to share those. we can no longer upload several terabytes of data via the web and share it, let's say, with our colleagues in Brazil. I mean, it's almost impossible. And then it's collecting data all the time. So this is why SpaceNet and also other challenges are moving to the cloud, like the Amazon cloud or other clouds. And we need to think of new ways how to do that without people having to pay for access, because then it's a paywall again, and only privileged people can access the data and so on. So I think I would see, as a community, we need something like a community cloud or something that is running, I don't know, at ETH University or in Sao Paulo or in Minas Gerais, and where we as a community, we maintain, we pay for it, and then everyone gets access, and all the data is there, so no one has to download. So just as an idea. So then in Switzerland, just on the side note, there's a strong push for open access. So for example, when I can say so, I believe this typical publishing houses, Springer, Elsevier, and so on, they make a lot of money with doing very little work from my point of view. We're the scientists, we do the most. And in Switzerland, we now negotiated that any Springer and Elsevier publications, all of them are open access. So, and the Swiss institutions don't have to pay extra for that. It's all open access now. And I think that's very important too. That everyone, although of course now it becomes less an issue because at least in computer science, most publications are in archive anyway. But still, I think open access publications and open access to data and source code is absolutely essential for progress, and also such that everyone on the globe, no matter where people are working, where they are based, if they're in Ghana or in Switzerland or in Brazil, they can do really cool research.
Thank you. I think in the same way. I hope in the near future we have more shared data, algorithms, etc. Thank you.
Thank you, José. Mateus?
Yes.
You are quite excited to ask something, right?
Yes, I have a question about multimodal data and also crowdsourcing. In your opinion, what are the main challenges of working with crowdsourced data in union with remote sensing that sometimes provide completely different types of data?
So, I mean, so we work with crowdsourced data that is app sourced, right? So it's some people that collect images. We have, for example, a project going on for biodiversity mapping that I didn't talk about today with the iNaturalist app, and we have another app in Switzerland. The problem is that there are strong biases in crowdsourced data due to several underlying effects and causes. For example, if we task people to take images of plant and animal species, one thing is that people they like the beautiful things, right? So we get a lot of flower images, but nothing from insects. Right? Although insects are just as important or more important. So we get very long-tail distributions for the classes. A lot of training data for very few classes, and then very few training data for the most thing. So that's one. Then another bias is a geospatial sampling is just based on how can I access something. So in Switzerland, if you go to the very high alpine regions, there's not much. People cannot go into the snow up to 4,000 meters, at least not many, and collect data. And then, of course, it's biased towards urban places. So we have a data set of France from a crowdsourced app, PlantNet, and the place with the biggest biodiversity and most samples is Paris, the city of Paris. So it's just because people have the app, they go outside into some park and they take a photo, that's it. It's just where most of the people live. So that's another bias. So I think, yeah, and then it's a matter how to correct the bias. So we are currently working on a project where we have this big crowdsourced data set, biodiversity in Switzerland, which is very biased with many biases. And we have a much smaller data set, which is unbiased, which was biodiversity sampled from our colleagues from environmental sciences, where they have a regular grid for Switzerland and they revisit a couple of years. So now the idea is to sort of get rid of the bias of the big data set using the small data set while still leveraging on this huge amount of data that comes from the big data set. But it's ongoing research. But it's a very relevant question. Yeah.
Thank you.
So thank you, Matteo. So we have one more question from the audience. From Anderson, is saying that in his doctoral research, he's seeking to access the level of sustainability, right, in urban cities using artificial intelligence. And yeah, do you recommend any specific approach to measure sustainability? Have you worked on that?
So I think I would first ask a question back, what do we understand under sustainability? Because sustainability, same as artificial intelligence, is such a buzzy umbrella term, very fuzzy, and that everyone is using, and that has lost a bit of its meaning from my point of view. But I don't want to, I think it's a very relevant question. I think if you, let's say, the first thing is specify what do you want to measure. What do you want to measure? Biomass. Do you want to measure canopy cover, the amount of greenness, for example, vegetation cover? Do you want to measure emissions, CO2 emissions, for example, something like this? And if you go for something like this, so you say, for example, well, I want to measure how much vegetation is in my city. First thing is the semantic segmentation, right? So you estimate, okay, how much vegetation, what is in my city? If you want to go for biomass, then you need to factor in the height of the trees and so on, right? Then you need some LiDAR data, or now GEDI data, for example. You need to factor that in. If you want to be very bold and work with your colleagues from climate research, then ask them for their models. Yeah? So how do they predict air flow through the city based on a digital surface model and together with rainfall, and combine the outputs of your semantic segmentation with their model. And you might even want to use some of their input data also as input for your model or as an additional constraint, and then it goes to physics consistent or physics constrained deep nets, right? So if you want to say, I really want to know, let's say, have a sustainability index for my city, and you have as input the models from my colleagues from climate research, I have a semantic segmentation, a land use cover, and so on. Then you can have a model and try to learn it and have several constraints, right? So I have, I don't know, some maximum index, and I have a constraint on maximum air exchange and flow and emissions, CO2 emissions for a particular city, and so on. That would be my answer. So no solution, but some ideas.
Yeah, it's kind of broad question, right? So maybe we have one last question. Maybe, I don't know, Jose or Mateus, do you have any more questions?
I have one. If we have enough time, I have one. At least one.
Yes, go ahead.
I made a quick search about the use application of deep learning, machine learning in general, uses the spectral libraries like NASA, Landsat, USGS. There is a few publications using this. If there is any reason for that, is a research area to be explored in the near future.
So I see a lot of potential in that direction, to combine what we did already in the past and what we understand well as spectral libraries, also hyperspectral imagery and so on. So really knowing about spectral signatures of particular, I don't know, cocoa plants, for example, or something, or soy or something, marrying this physics knowledge with deep nets, and or using the spectral libraries really, let's say, as a lookup table, and having just a deep net that takes out that spectral signature that fits best to what you see in a remote sensing image and so on. So and I see this is a big emerging topic, because your predictions in deep nets, if you marry it with a spectral library, for example, really get the physics constraint. They get much more meaningful, because it's not just some deep net black box prediction, it has really a meaning, and you can tie it to the physics. A second thing is, my hope would be you need a lot less training data, because you know a lot about the spectral properties of a lot of materials and plants and so on already. So we might get rid of this nasty task of having to label vast amounts of areas in aerial images or satellite images manually as training data. So my hope would also be that we can get rid of this effort. We can have, let's say, models with the same predictive power, but a lot of less training data. So you could frame it as a weekly supervised task or something like this. Yeah. And then a third point is, I think we will see a re-advent of a generative model. So GANs is a deep net approach. At the moment, everything is discriminative. When I started my PhD, a lot of things were generative, maximum likelihood and so on. Then everything, conditional random field, also was discriminative. We say, okay, discriminative, this is great. And now deep nets are also discriminative. But I think there's true value looking now into generative models back again, because they have a richer modeling representation of the joint distributions. And I think there's a lot of potential there. And also with respect to spectral libraries, simulations of the spectral properties, radiometric calibration, and so on. So yes, I absolutely agree. I think that's a fantastic direction of research.
Okay, thank you very much.
Nice touch, Jan. So I think we're unfortunately coming to the end. It was like, I think it is an exciting topic of research. And also like to thank the audience, the moderators, Jose, Mateus, the organizers, Jefferson, Veraldo, and also vielen Dank, Jan, for your presentation. Yeah. It was very nice indeed, with very state-of-the-art results. Very exciting. So once again, thank you all, and have a great day, and hopefully in good health for everyone. Right? Thanks you guys.
Thanks a lot, everyone. Take care.
Take care.
Bye-bye.